Have you ever wondered how your phone knows it's you or how an AI can just dream up a piece of art out of thin air? Well, the magic behind all of that is something called an artificial neural network. And today we're going to build one from the ground up, piece by piece, to really understand how a machine can actually learn to think. So, here's our game plan. We're going to start with the big idea that sparked it all, the brain-inspired model. Then we'll zoom in and meet the star of the show, the artificial neuron. After that, we'll see how you connect them to build powerful networks, figure out how these things actually learn, and finally, we'll uncover the secret sauce that makes it all possible, the backpropagation algorithm. Okay, so first things first, where did this wild idea even come from? Well, it all started by looking at the most powerful learning computer we know of, the human brain. I mean, this is the million-dollar question, right? For a long time, we tried to program computers with tons of if this, then that rules. But that's super brittle. So the real pioneers of AI asked a much better question. What if, instead of programming rules, we built a machine that could learn from experience, kind of like we do? And that right there is the fundamental idea. With a neural network, you don't hard-code a cat has pointy ears, whiskers, and a tail. No, instead you just show it thousands and thousands of cat pictures and the network figures out the important patterns all by itself. So, if we're going to build an artificial brain, we've got to start with the most basic building block, right? The artificial brain cell. And here it is. This is an artificial neuron, sometimes called a perceptron. Now, it's not made of biological stuff, it's really just a little math function that acts like a tiny decision maker. One on its own isn't very smart, but it is the fundamental unit that makes up the entire network. And every single one of these neurons goes through the same four-step dance. First, it gets a bunch of inputs, and each one has a weight, which is just a number that says how important it is. Second, it adds up all those weighted inputs. Third, something called an activation function decides if that combined signal is strong enough to pass on. It's kind of like a gatekeeper. And finally, if the signal is strong enough, it fires off an output to the next set of neurons. That simple cycle happening thousands of times is the core of everything. So a single neuron is, well, it's a pretty simple little machine. It can really only make a basic decision, kind of like drawing a single straight line to separate things. But the real world, it's way more complicated than that. To solve real problems, we absolutely need strength in numbers. And this is the light bulb moment. Look at that difference. A single neuron is stuck with a straight line, but when you start connecting them into a network, they can create these incredibly complex, squiggly boundaries. The real intelligence isn't in any one neuron. It emerges from the way they're all connected together. Now, this shows you the most common way to set them up, a feed-forward network. It's called that because information only flows in one direction. It starts at the input layer, which just takes in the raw data, like the pixels from a photo. Then that data flows through the hidden layers. This is where all the heavy lifting and complex processing happens. And finally, it all comes out the output layer, which gives you the final answer, like cat or not a cat. Okay, so we've got our network all built. But here's the thing. When we first create it, all those connection weights are just random numbers. It's basically an empty brain that doesn't know anything. The next step is to teach it. And we call this process training. It's a loop. We show the network an image, and it makes a guess. Then we look at that guess, compare it to the real answer, and figure out the error, how wrong it was. Then, and this is the cool part, we use that error to make tiny, tiny adjustments to all these connection weights, just nudging the whole network a little closer to the right answer. Now do that millions of times, and pretty soon the network actually learns. So the mathematical engine that's making all this happen is a really clever algorithm called gradient descent. You can think of it as a smart, systematic way to figure out exactly which direction to nudge all those weights to make the network's error go down. And here is the absolute best way to picture this. Imagine that all the possible settings for your network's weights create this giant hilly landscape. The high peaks are where the network has a huge error, and the deep valleys are where the error is super low. Our goal is to find the lowest possible point in that entire landscape. Gradient descent is our strategy. No matter where you're standing, you look around, find the steepest downhill direction, and take a small step. Then you do it again and again and again until you've walked all the way down into the bottom of the valley. Okay, this brings us to the final and maybe the most important piece of the whole puzzle. You see, for decades, this whole walking downhill idea kind of worked for small networks, but it just completely fell apart on bigger ones. And it was because of one really, really tricky problem. Think about it. When the network gets an answer wrong at the very end, how in the world do you assign the blame? Which one of the thousands or maybe millions of connections buried deep inside the network was the most responsible for that mistake? Cracking this credit assignment problem was the big breakthrough that really unleashed modern AI. And the solution is an incredibly clever algorithm called backpropagation. Don't let the name scare you. At its heart, it's just a really efficient way to use calculus to figure out exactly how much each and every single weight contributed to that final error. This visual lays out the whole cycle perfectly. First, you do a forward pass, just like we talked about, where the data flows through and you get an output. Second, you calculate the error. Third, and this is the magic step, you do a backward pass. You take that error signal and send it backward through the network, from the output all the way to the input. As it goes back, the algorithm assigns a little bit of blame to every weight it passes. And finally, you update all the weights based on how much blame they got. This forward and backward dance is the engine that powers all of modern deep learning. So let's just recap what we've built here. We started with those simple little calculators, the neurons. We saw that arranging them in layers is what gives them real power. We figured out that training is just the process of tweaking weights to reduce error. And we uncovered that backpropagation is the genius algorithm that makes the whole training process fast and efficient. And that's really the thought I want to leave you with. Everything we've just gone over, these are the exact same principles that are the foundation for all the crazy AI you see today. When you take this idea and just scale it up, way up, from a few layers to hundreds of them, that's when you get a deep neural network. And that's what can translate languages in real time, generate stunning art, and even drive a car. It all starts right here with these simple, elegant building blocks. Thanks so much for digging into this with me.